Great. Welcome, everybody. We are very fortunate today to have Dr. Eric Sherby chipping, pitching in with the class and helping us. He is a great friend and supporter of our activities. But more than that, he has a long experience. He has a PhD in physics, and he is the chief technology officer of Iris NDT, that is a global company. And for many years, he was the chair of the group on NDT at the International Institute of Welding. That it is the group where like the great minds from all countries come together to discuss issues and develop technology into the future. It's it's an amazing fortune that Eric is Canadian and Eric is in Edmonton, and he's our friend. So this is one of the great things we have for being at U of A, and that you have for taking this class. So thank you, Eric, for helping us with this. I treasure all the help you give us. Floor is yours.
All right, no, thank you very much. So I'll just get right into it. I think Patricia kind of covered my background. I'm a physicist that got into NDT a long time ago, and I've been in the Alberta industry for a long time and other countries as well. So this is a lecture I've given a couple of years now, and I usually start by defining what NDT is. So NDT is non-destructive testing, and my background is physics, and I know all of you have taken physics, so I'll kind of talk more in a physicsy kind of way, but NDT is sending a field into some sort of solid. So steel or aluminum or whatever. And fields they could be high energy photons, they could be, you know, that would be radiography, it could be phonons, which are lattice vibrations, which could be ultrasonics, it could be electromagnetic fields, magnetic fields. So what we're doing is we're sending a field into a component, and we're looking to see if that field is disrupted by discontinuities. That's what NDT is. And then there's a set of codes that tell us if that discontinuity is a defect or not. So discontinuities are in every material. They're all over the place, but we don't want to be telling customers they have to repair discontinuities. We want them to be telling them when they have to repair defects. And defects are when discontinuities grow to a size that they're a problem for fitness for service. And it's the codes that tell us that. So this talk is going to be about the different NDT techniques and how the codes tell us whether that discontinuity we found is a problem for fitness for service. In other words, whether the part is going to fail or not with that discontinuity. And from an engineering perspective, the goal isn't to have enough background for you people to go out and do inspections, but the goal is to understand them well enough that you can use non-destructive testing when you're out in the workforce to make sure that components are fit for service. And that could be bridges, it could be airplanes. In Alberta, that tends to be oil and gas infrastructure. Mining companies have large infrastructure, petrochemical companies, and then the municipal space, so bridges and buildings and things like that. So this talk is not for NDT people, it's for engineers that one day will have to use non-destructive testing for your jobs. And what we're going to do is we're going to cover these basic techniques, but the techniques are going to be covered from a perspective of what an engineer would need to know to do their job. So I'm going to start with the physics or kind of the basics of these techniques. And then I'm going to get into how we use them in Alberta, and that's kind of an Alberta specific section in all these, so what we use them in Alberta, not in other industries like say aerospace that we don't have here. And then we're going to get into kind of important stuff for you people, and that's how these techniques are calibrated, because we need to be able to calibrate them properly. So we want all of these techniques to be insensitive to small discontinuities because they're not a problem for failure. We don't want to be telling customers they have to repair small discontinuities because they're not going to lead to failure. So we want to be insensitive to really small defects or discontinuities and we want to be sensitive to ones that are a problem and will lead to failure. And that's where calibration comes in. And then I'm also going to talk about the code requirements of all these techniques, and that's good practice. So if you end up needing some of this work done, the code says what good work is and what good work is not. So the code tells how to calibrate, how to set up, what variables need to be included in a report, how the work is supposed to be done for good quality of work. And then the last thing I'll talk about is the advantages and limitations. So all of these techniques have advantages, which everyone's really happy to talk about, but they also have limitations. And it's really important for engineers to know what the limitations of these techniques are, because I've just seen a lot of bad work in industry where engineers call for a certain inspection technique to find a defect, and you have no chance of finding it because it's the wrong technique. So I'll wrap it up with a bit about the advantages and limitations, and I'm going to do that for each of these inspection techniques. So this is an awful lot of material. It's coming pretty fast for us to make it through in one lecture. If you got any questions, please just jump in in the chat, or just jump in with the audio and ask. All right, so the first one I'm going to cover is magnetic particle inspection. So in Canada, we call that MPI. In the US, we call it MT, which is magnetic testing. And MT is common in Alberta because we use American codes for most of the work we do. So you'll see that term MT. And this is a technique that only finds defects that break the surface. And it can only be used on ferromagnetic materials. So it can't be used on non-magnetic materials like stainless steels or aluminums. It has to be things like carbon steel. And with this technique, all we're doing is we're magnetizing the volume of the material, and that magnetic field is also with the surface of the material. And if there's a surface breaking crack or defect, it's going to expel some of that flux. And then we're going to put a powder or some sort of magnetic material on the surface, and wherever that flux is expelled, the powder will congregate and will visually see the defect. So in Alberta, most of the applications we do have that yoke, which is the red thing on the right. So all that is it's one of those prongs that sticks down as a north terminal or a north pole, one's a south pole. You touch it on the surface and it generates a magnetic field in the part. And it's very flexible. We can use it in all kinds of constricted areas. We can use it on different configurations of welds. And it's good in the cold. It's good in the heat. It's just easy to use. So most of the work is done using that coil on the right. And we also have big benches like on the left, but those aren't as common because most of the work in Alberta is done out in the field, which is good for those yokes. And then these are what the magnetic particles look like. At Iris NDT, we just buy them by the truckload and we mix all of it ourselves. But that's just fine powder that's magnetic. So it's going to congregate at those north-south magnetic poles where there's defects on the surface. So for magnetic particle, we have two ways of doing it. We can do what's called a dry magnetic particle inspection. And that's where we spray a white paint on the surface and we use a powder that's dusted on the surface. And that powder will congregate where we have the defects that break the surface, and we'll see it. We'll visually see the defect. And this is good for rough surfaces, and it's good for high temperatures because there's no liquids there to boil off, so we can use it at high temperatures. We also use wet magnetic particle inspection, and that's a higher sensitivity technique. And we got a question here. So what is the powder made of? I think it's iron oxide for the most part. That, it's small magnetic particles, and I think a lot of it's iron oxide. So with wet magnetic particles, we use the same iron oxide as the magnetic particles, but we put it in an oil or a water, and it's fluorescent. So this has to be done in the dark, and then we use an ultraviolet light to visually see the defects. So wet magnetic particle is more difficult to do because you can't have light and it can't be done at high temperatures, but it's more sensitive. And in NDT, sensitivity is the ability to see small defects. So it has better ability to see small defects. With calibration, there's two parts to it. We have to calibrate the yokes. So that just has a magnetic field. So those yokes, if they're working properly, they can lift a certain amount of weight. So that's when, before a technician goes out and does this work, they calibrate based on the amount of weight. That has to be able to lift that amount of weight. And then the black lights, which are the ultraviolet lights, have to emit a certain um, density of radiation. So you have to have enough ultraviolet light to see the defects. So that's what the technicians will do before they go out. They'll calibrate those and they'll be on the report that they meet calibration standards. So codes, this is kind of going to be the way the codes go for all these techniques. So the main code that's used is the ASME code, which is the American Society for Mechanical Engineers. And most of that code is about construction. But Section 5 is all about non-destructive testing. And Section 5 is built up of many different articles that all deal with the different types of inspection. And Section 5 is procedural. So ASME Section 5, Article 7 is the part that deals with MPI inspection. And when I say procedural, what I mean is it it tells you how to configure the inspection, how to set it up, how to calibrate, how to do the inspection when you're in the field, and what variables need to be included in the report. And then ASME Section 8 has the acceptance criteria. So like I said earlier, we don't want to be so sensitive that we're calling all kinds of small defects that aren't a problem for fitness for service, but we also don't want to be so insensitive that we're missing big defects that will lead to failure. So Section 8 tells us what is acceptable and what is not once we've done our inspection. And essentially it says that linear indications like cracks are usually rejectable if they're more than a certain length. And rounded indications are rejectable if there's groups of them or they're bigger than a 3/16 of an inch. And that would be things like porosity that have come to the surface of the weld and frozen in. And then B31.1 and B31.3 refer back to ASME. So those are the piping codes. They, they don't have their own procedural part. They refer back to ASME. And then this is the advantages and limitations. So with MPI, that's probably the most common technique you're going to see in Alberta. It's cheap, relatively cheap. It's fast. It can be done in all weather conditions. There's lots of people that are trained in it, and it's great at finding surface breaking defects. So it's used all the time for new fabrication, which is looking for defects that may be there in the welding process with new parts. And it's used all the time for in-service inspection. And that's things like looking for vibration to see if you have fatigue cracking. Limitations, you have to clean the surface. It's not going to find anything subsurface, and there's temperature limitations. So that's a quick summary on MPI. And that's, like I say, that's probably the most common technique we see in Alberta. So the second technique we're going to talk about is liquid penetrant inspection, which is LPI in Canada or penetrant testing, PT in the US. And with those ASME codes, it's all PT. And this is the same kind of deal as magnetic particle inspection. It only finds surface breaking defects, and usually it's used on non-ferrous materials because you can't do MPI on that. You can use it on both ferromagnetic and non-ferromagnetic materials, but it's more expensive than MPI, so we typically only see it on non-ferromagnetic materials. So this is really a capillary action type thing where we put a liquid on the surface that has a low viscosity. So we clean the surface really well. We put this chemical dye on the surface. We let it sit for a while. Capillary action will draw it into any surface breaking defects. We just wipe the excess dye away from the surface, and then we use a developer to show us where the defects are. So LPI it's a similar inspection to MPI in that it will only find surface breaking defects, but the physics is different. It's a capillary action inspection rather than a magnetic inspection. So with this, it's really the same as MPI. There's a visible penetrant, so that's just visible where you use it on a surface and you see the cracking, and then there's a fluorescent penetrant, and that's the same kind of deal as MPI where you need an ultraviolet light to show where the defects are on the surface. They're both visual, so it's just done visually. You just look and see where the penetrant is. And like with MPI, the fluorescent penetrant is more sensitive. It takes longer to use, but it's more sensitive. And this is very similar to MPI. So with with this one, instead of being Article 6, which is MPI, this is Article 7 is MPI, this is Article 6. So ASME Section 5, Article 6 is the procedural part, and that's the one that tells how do we calibrate, how do we do it in the field, what do we need to include in a report when we do the inspection, the same kind of stuff. And then the acceptance criteria are in Section 8, and that's the same as with MPI. And like MPI, B31.1 and B31.3 refer back to ASME. So as an engineer, you go, if you want to know if that LPI inspection was done right and the report was done right, you go to Article 6, and that tells exactly how it should be done, exactly how it should be calibrated, exactly what needs to be in a report. That's how you would do an audit of an LPI report. And then advantages and limitations are a little different than MPI. With LPI, it's a liquid, so we can do it on any material shape. It's inexpensive and relatively fast, but it's slower than MPI and more expensive. So we tend not to do it. If we do, we'll do MPI if we can. It's only sensitive to surface breaking discontinuities. It's very portable. And then as far as limitations go, surface cleanliness is critical. You have to clean the parts far more than MPI because you have to clean them enough that the die can penetrate any of the surface breaking defects. So all paint, everything's got to come off the surface down to bare metal. It's not going to find anything below the surface. The materials obviously have to be non-porous, and then there's more stringent temperature limitations. You have to have the right viscosity or it won't soak into the surface breaking cracks. So that's a quick rundown on LPI. Now we're going to talk about ultrasonic testing. So there's two main techniques for detecting surface breaking defects, and that's MPI and LPI. And then there's two main techniques for inspecting the full volume of the weld. So not just the surface, but everything subsurface. And UT is one of those. So with ultrasonic testing, what we're doing is we're sending high frequency sound waves into a material, and we're generating those sound waves with a piezoelectric crystal. And then we're using Snell's law. Snell's law is just refraction. So if we want to generate an angled sound beam, we just put a wedge on it like that bottom picture, and we get an angled sound beam in the material. And the angle was based on Snell's law, which is, Snell's law is kind of what you see in Pink Floyd's prism. It's just you get the different refraction based on different angles. So with UT, we have to make, there's a couple of things I see that are result in bad work. So with ultrasonic testing, we have to have isotropic materials. And carbon steels are almost always isotropic. Austenitic steels aren't. So you have to be real careful when you do ultrasonic testing on austenitic steels. That can lead to all kinds of bad work being done. And the code talks about that. That's in the ASME code. So with ultrasonic testing, all we're doing is we're sending ultrasound into the material, so maybe a carbon steel. If there's a defect there, some of the sound's going to reflect back. So that sound reflects back to our transducer. We see a signal, and the codes tell us how to interpret that signal as maybe a discontinuity that's not going to lead to failure, or maybe it's a defect that needs to be repaired. So that's what we're doing with ultrasonic testing. Now, the main display in ultrasonic testing is an A scan, and that's just that on the y-axis has ultrasonic sound pressure. So that's just the size of the signal. And the scale on the x-axis is time, or because we know the velocity of the wave, it's distance into the material. So that's the main display you're going to see. And typically, the bigger signals you get are from bigger defects. Smaller signals are from smaller defects. So that's typically how this inspection is done or interpreted. As an engineer, you're gonna see these. It's really common to do thickness readings over a surface area and then show a map of them. And that's what this is. So what we've done is we've taken a UT thickness transducer, which tells us the thickness of the material, and we've moved it across an XY pattern on, say, a pressure vessel. So maybe there's a part of a pressure vessel we know has some wear or some corrosion. We move it across that surface and it generates a picture of the wall thickness of that pressure vessel. And the A scan is in the bottom left. So that's just the sound pressure on the y-axis versus depth on the, or time or depth on the x-axis. The C scan on the upper right is where we just use color to denote thickness. So blue is normal thickness, yellow is some corrosion, red is a lot of wall loss, a lot of corrosion. And then the B scan and the D scan are cross-sectional views. So that's where those red cursors are. That just shows a cross-sectional view of the wall thickness of the pressure vessel at that location. And this is data that's good for engineering. So this is perfect for fitness for service. And fitness for service is where we do an analysis of the pressure vessel and we look at that data and we determine if the pressure vessel will hold the pressure and is safe to operate with that corrosion there. That's a calculation that's just done all the time. And this is a very common inspection where the data is used for determining if you can still operate that piece of equipment with that corrosion there. So so there's a couple of ways this is calibrated. So the first part of the calibration is we need to know the velocity of sound in the material, because we can't position defects properly unless we know the velocity. So these are the calibration blocks that we use to set the velocity, and then we can calibrate that probe so we get the proper depths when we do an inspection. So we know what the thickness of the pressure vessel is 10 millimeters and not 20 because we need to calibrate it. So that's the first part of a calibration when you do ultrasonic testing, is you have to set the material velocity, and the probe delay is how much time the sound takes to get out of the ultrasonic transducer, because you don't want to take that into consideration when you do the inspection. You just want to know the material you're inspecting, not the probe. So that's a y equals mx plus b type calculation, and that's the first part of a calibration when you do ultrasonic testing. The second part is the sensitivity. So once we've calibrated the transducer and we know the y equals mx plus b, or we know the velocity and the delays, we have to make sure we have the right sensitivity, because we don't want to do an inspection and end up calling very small defects because they're not a problem for fitness for service. We also don't want to miss very big defects. So we need to do sensitivity calibration. So we're allowing defects or discontinuities to stay in the material that are fine, and we're making sure the customer knows when there's repairs and it's not safe to operate that vessel. And that's what this calibration is. And it uses a block called an ASME block. And that's part of the code. It's described in the code. And that's just allows us to set the amount of sound pressure, the y-axis of that graph I showed you. So we can do a proper inspection and we know what sensitivity we have. And then a distance amplitude correction curve. As that sound goes farther and farther into a material, it attenuates and it spreads out. So we have to do that sensitivity calibration at different depths. So we get the same sensitivity at close to the probe as we would far away from the probe. And once we've done those two parts of the calibration, the ultrasonic system is calibrated and we can do the inspection. And you should always see on any report that does any type of ultrasonic inspection, there has to be information and description about how the calibration was done. So in Alberta, a lot of what we do is manual UT, and that's just where the probe is held by someone's hand. They're interpreting that first graph I showed you, which is the sound pressure versus the time, and you're getting a paper report that describes it. And then there's also fully robotized systems where you put them on a piece of equipment, they move on their own, they gather all the data, it's 100% repeatable, and it's 100% recorded on a computer for analysis and archiving. And those would be, that would be a mechanized testing, so AUT. AUT stands for automated ultrasonic testing. So a lot of the work would be manual UT because that's less expensive. And then some of the work would be AUT, where we have to, a customer wants to do a full fitness for service and they want the data archived. If, for instance, they're doing inspections, you know, maybe they've got a defect they're monitoring every couple of months, they would do an AUT inspection where they can compare the full data sets and have full reproducibility. So with the code requirements, it's very similar again. So ASME section 5 is the procedural part, and for ultrasonic testing, it's Article 4. So Article 4, kind of like the last two examples, Article 4 tells the technician, how do we set the ultrasonic system up? How do we calibrate the first part of the calibration for the velocity and the delays in the probe? How do we do the second part of the calibration for sensitivity? How do we perform the work in the field? And what do we need to include in a report? That's all in ASME Section 5, Article 4. Now, ASME Section 8 has the acceptance criteria for ultrasonic testing, and I put it down here. So for ultrasonic testing, whenever a technician finds a crack, lack of penetration, or incomplete penetration in a weld, it's unacceptable. Those are all stress risers, and those are all need to be repaired. And then for volumetric defects like slag and porosity, signals greater than DAC with a length criteria are rejectable. And that comes out of ASME Section 8. And then, like the other examples, B31.1 and B31.3 refer back to ASME Article 4. So those are the piping codes. So advantages and limitations. Ultrasonics is really good at finding linear flaws. So for in-service inspection, where cracking is something you expect in a weld, it's really good at finding it, or in your base material. Automated techniques are really good. Ultrasonics is really your only choice for fitness for service because it gives the depth information. Okay, so we've got a question here. The question is, what do signals greater than DAC mean? So with that, what we're doing is these lines here are from the calibration block. So when we're doing an inspection, we have a certain thickness of plate or of weld, and that we go off to the code, and the code tells us how big the side drilled holes are. So the side drilled holes are how we set the sensitivity of the ultrasonic system. So maybe they're 3mm side drilled holes for a block that's, or for a plate that's 1/2 inch thickness. And then we set that DAC at different depths. So this would be close to the probe, so the sound pressure's high. And then as your sound attenuates, you have to set a DAC that's lower because you're, as I said, the deeper into the material you go, the more your sound dissipates. So you set a curve that represents what that 3mm side drilled hole, how much sound amplitude that reflects at different depths. And you go compare all your defects to that. So if you have a volumetric defect like porosity, and it actually produces more reflected energy than this DAC curve, then it's rejectable. If it produces less than that DAC curve, it's acceptable. That's what that means. So I hope that answered the question. I guess it's hard with Zoom to know, but hopefully that answered the question. And then the other advantages of ultrasonic inspection are that it's good on thick materials, but it's not so good on thin materials. So when you get to really thick welds, it's really what you do 100% of the time. You want to always do ultrasonic inspection. For limitations, you have to do a fair amount of surface preparation before you do ultrasonic inspection because you have to couple the sound in, and that coupling has to be consistent. So you can't be on a bad surface. It's difficult at high temperatures. Like I said, you can't do it well on coarse grain materials like stainless steels or ink alloys. And if you do manual UT, you've got no permanent record. So those would be the advantages and limitations of ultrasonic inspection. And like I say, with with coarse grain materials, that's an example of bad work. You know, customers will call for an ultrasonic inspection, someone will come out and do it, but it's not clear there's any value there. So as engineers, you need to know what it's good at, but more importantly, you need to know what it won't do. All right, with radiographic testing, so I said we've got two techniques that can give us a full volumetric inspection. So that'll inspect the surface, but also the whole volume of whatever we're inspecting. And ultrasonics is the first one, and radiographic testing is the second one. And with radiographic testing, we've really got all the advantages and limitations are almost exactly the opposite of ultrasonics. So the two techniques fit really well together. So with radiographics testing, we have film. The film has different speeds. So grain size, that would be like an ISO speed on a camera film. We take high energy radiation and we expose that film. And that gives us a picture of the weld or the pressure vessel or pipe or whatever we're inspecting. We tend to use lead shielding to protect so with, I'll just answer the question. The question is, what is meant by fitness for service? Aren't NDT methods checking that the defects won't interfere with service? So with non-destructive testing, we strictly detect the defects that are there. That's all we do with non-destructive testing. We don't make any comments on whether that defect is fit for service. All we're doing is we're inspecting something and we're coming back to our customer saying there's a defect there of this size or there isn't a defect there of that size. Now, with new fabrication, so when something is made the first time and it's brand new, the codes tell us exactly what is acceptable and exactly what is rejectable. So we do our inspection, we find a discontinuity or a defect, and we can say exactly whether that defect is acceptable or not. So whether it has to be repaired or not. As soon as we get it, as soon as that component goes into service and it's being used, the codes don't apply anymore. So all we do is we go out and we do an inspection and we find something, and the customer has to determine if that's acceptable or not. And acceptability would be, is that component going to continue being able to be serviced? Can you continue operating it in the service it's in, or does it have to be repaired because it's going to fail? And fitness for service is the way that they analyze that. So what they do is they take the component, they take the material strength, they take the defect size, they take the pressure, the temperature, and everything, and they do a calculation that says maybe that component can be operated forever with a defect like that in it. Maybe it can be operated for another year until they have a regular shutdown and they can fix it. Or maybe it's not safe and they better shut down immediately. And that's what fitness for service is. It's taking all the material properties, it's taking the geometry properties, it's taking the information from an NDT inspection, which is where your defects are, and it's doing a calculation to determine if you have to shut that piece of equipment down or you can continue operating. And the customers all want to continue operating. None of them want to shut down. They want to know if they can continue operating till a regular maintenance interval rather than having to do an emergency shutdown, which is difficult. Does that make sense? All right, so we'll keep going with RT. So with radiography in Alberta, we can generate the radiation with X-ray tubes, but that's not so easy in our environment because it's cold out and we've got a lot of work in difficult environments, and X-ray tubes are delicate. So most of the work we do has what we call gamma sources. So these are small radioactive pills that produce radiation. And there's three of them that are typically used in our business. One is cobalt-60, one is selenium-75, and one is iridium-172. And iridium is by far the most common one. And cobalt-60 has much, much stronger energy, and it can penetrate through much thicker materials. And selenium is the weakest energy, and it can only penetrate through very thin materials. And it's just a physics thing. So the shorter the wavelength of your radiation, the higher the energy and the deeper the penetration. So cobalt-60 has the shortest wavelength of those three sources. It has the highest energy photons, and it can penetrate the most material. Iridium is in the middle. So in our industry, we don't really see selenium much in Alberta. Cobalt 60 is used about when steel is about 2.5 inches and up, we use cobalt 60. And the thickest materials I've ever inspected are a foot. So almost 300 millimeters of steel. And then iridium is used from, 2.5 inches and down. So iridium by far is the most common one you see in our industry or in Alberta. So with radiography, all we're doing is we have an X-ray source or a gamma source on one side. We put the weld or the pipe or whatever we're inspecting in the middle, and we put the film on the other side. We allow the radiation to penetrate through the weld or whatever we're inspecting. It hits that film on the far side. The code tells us how long we have to allow that to properly expose the film, and then we do a chemical processing on the film. And I know with cameras all being digital these days, you guys probably have never done this, but it's just a chemical processing where we take a piece of film and we reduce the silver and we get a radiograph out of it. And with radiography, there's something called radiographic density. So you want the grayscale to be right. So the picture on the bottom, the density is too low, so it's not had enough radiation to properly expose it, and it's white. You just can't see much in it. The one on the top right, that's been exposed with too much radiation, so it's too dark, and we can't really interpret it. So the ASME code tells us what the correct density is, which is that one on the top left, and you can just see a lot more in that image because it's exposed properly, and that's radiographic density. The other thing we deal with is sensitivity. So just like with ultrasonic testing, we had the second part of that calibration where we dealt with sensitivity with the ASME block. With radiography, we need to know what the sensitivity of the technique is. So just like the other techniques, with radiography, we don't want to be telling the customer there's all kinds of super small defects, and we don't want to be telling them they're rejectable, but we also don't want to be so insensitive we're missing big defects that will lead to failures. So we do that with something called an IQI, which is an image quality indicator. And those are just wires of different diameters. So typically with radiography, we want to be 2% sensitive. So if, say, our plate is 100 millimeters thick, we want to be able to, the minimum variation in thickness we want to see is 2 millimeters. And that's what those wires do. We need to be able to see we put those wires over the weld, just like in that picture at the bottom, and we need to be able to see roughly a 2% sensitivity when we do radiography. And that makes sure we've got the right sensitivity. So we're sensitive to things that are a problem, and we're insensitive to things that are so small they're never going to cause a problem. So with weld exposures, this is the same kind of thing I just showed you. When we're doing welds, we can shoot them with the source right up against the pipe and the film on the far side, which is that contact exposure on the far left. We can also shoot them either in a superimposed or an elliptical exposure, which is when this radiographic source is further away. And typically we do contact exposures for all the bigger diameter pipe and elliptical exposures for the small ones. And then this is very similar to the other. This is almost exactly the same as ultrasonics. And so it's section 5, article 2, that is the procedural part of it. So that's the same as the other techniques where that tells us how to set it up, how to calibrate radiography, what we have to report in a report, how we do the weld inspection, whether it's contact or one of those other techniques. All of that is in article 2, section 5. And then section 8 is the acceptance, and that's very similar to ultrasonics. And like on ultrasonic inspection, the piping codes refer back to ASME. And then the advantages and limitations are almost exactly the opposite of ultrasonics. So with ultrasonic inspection, it's really good at finding linear flaws, but it struggles at volumetric flaws. Radiography is the opposite. It's really good at volumetric flaws, and it can struggle at linear flaws. With UT, the results are not always reproducible. With radiography, they always are because you have a permanent radiograph. With ultrasonic inspection, you have to do surface preparation. With radiography, you never do. With ultrasonic inspection, it's good on thick materials, but struggles on thin materials. Radiography is the other way around. It struggles on thick materials because you have to have long exposures, but it's super fast on thin materials. With ultrasonics, you get depth information. With radiography, you don't. So it's almost exactly the opposite of what ultrasonic inspection would be, which makes them a really good fit. So applications that are really good for ultrasonics may not be good at all for radiography and vice versa. So that's radiographic inspection. And like I say, my apologies for going quick. It's there's a lot here, so I'm just blasting through it. And it from an engineering perspective, the details aren't as important as knowing you can look in the ASME code to see what a good inspection is and knowing what the advantages and limitations are and what a proper calibration is. That's the things that from an engineering perspective are important. All right, so the last inspection that's part of the regular one. So there's 5 inspections that are governed by the Canadian government. So that people are certified, courses are given, and they control the certifications in Canada. And this is the last one of those 5 that the government controls, and that's eddy current testing. And this one is not done much in Alberta, and I'll talk about why later, but it's done for heat exchanger tubes, and we don't see it too much in our industry other than for heat exchanger tubes. So for this one, we're putting an electromagnetic field into the material, and it breaks down really nice with physics. The first technique was MPI, and that was a magnetic field. The second technique was LPI, and that's capillary action. The third technique was ultrasonic testing, which is vibrations in the lattice. The fourth technique was high energy photons, which is radiography. And this is an electromagnetic inspection technique. So it's kind of covering the different fields, physics fields we could use. So for this one, we're putting an electromagnetic field into the material, and we can only do it on conductive materials. So it can be done on steel, aluminum, titanium, things like that, but we can't do it on anything that's non-conductive. So we can't do it on composites and rubber and things like that. So this is mutual inductance. So all we have is this is exactly like a transformer. So we have a primary coil, which is our eddy current testing probe. We pass an AC current through that probe. And if that probe is close to a conducting surface, it generates an electromagnetic field in the part we're inspecting, and that causes eddy currents to flow in that part. And what we're doing is if there's no defect, the eddy currents will come to some steady state, and that's what we see. If there's a defect, it's going to disrupt those eddy currents, and we're going to see a change in our electromagnetic properties. So that's what eddy current is from a physics perspective. So this is how we would inspect a heat exchanger. So a heat exchanger has many tubes. The tubes tend to be really thin, and that's where we have maybe a hot product on one side and a cold product on the other, and we want to transfer heat from something hot to something cold. And we do it all the time in industry. That's a very common thing to have heat exchangers. And we need to inspect those tubes. So in this case, we have eddy currents that are flowing around the circumference of a tube, and they're in steady state. If there's a defect or a discontinuity, it forces those eddy currents into a different path. And by forcing them into a different path, it's disturbed them and it's changed the electromagnetic properties at our coil. And we see that as a change in resistance and inductance in that coil. So with eddy current testing, we're using something called a Lissajous plot, and that's really the inductance versus the resistance that primary coil is experiencing. And resistance is the real component of an impedance, and inductance is the imaginary component of an impedance. So really, it's the inductance has the phase information. So what we're doing is, or when a technician is doing eddy current, they're balancing the probe. So that they know kind of what the signal is on a part of that tube with no defect. If they see a change in that Lissajous plot, so the real versus imaginary components, then they have to interpret it as, a defect or a discontinuity. That's what we're doing with eddy current. Now, up until now, we've kind of been dealing with absolute calibrations. So with radiography, we were trying for 2% sensitivity on the full thickness using those wires, and that's an absolute thing. With ultrasonic testing, we're calibrating the y equals mx plus b, which is your velocity in your material and the delay in your probe, and then we're doing a sensitivity calibration, and that's absolute too. With eddy current, there's no absolute calibration. It has to be a a comparative technique. It's a comparative calibration. So all we can do for eddy current is we have to have a material that has exactly the same metallurgy, exactly the same heat treat properties, and we machine defects into that material, and then we calibrate our eddy current system based on those artificial defects in a part that has exactly the same geometry, exactly the same metallurgy, and exactly the same heat treatment. And then when we go into an inspection in a heat exchanger, what we're doing is we're comparing signals from that heat exchanger to that artificial calibration standard. So that's how we're calibrating eddy current. And that's a bit different than the other techniques because it's not an absolute calibration. It's strictly a relative calibration where if we don't get that calibration piece correct, nothing is correct. So it's really important to have the right calibration piece with the right heat treat properties, the right metallurgy, the right diameter, thickness, and everything. If you don't do that, the whole inspection is flawed. Now, the codes are a little simpler, so we don't use this so much in our industry. So the Article 8 deals with eddy current, but it just doesn't have the detail that the other articles have because it's not a common technique that we see in our industry. And we don't have acceptance criteria in ASME Section 8 because we never use it for new fabrication. It's always used for in-service inspection. So the code requirements for eddy current are a lot less detailed than the other techniques just because it's not used as much. And the main reason it's not used is because we can't penetrate thickness well. So the most of the components we use in the industries we have in Alberta are thicker, and eddy current just doesn't penetrate thick. If you can go 2.5, 3 millimeters deep into a part, that's really good. That you're doing well with eddy current if you do that, but that doesn't cover much of what we have here. So it's used for heat exchangers for the most part, and we just don't see it in other parts of industry in Alberta because it just doesn't have the ability to penetrate the kinds of depths we have. Where it's used a lot is the aircraft industry. So they tend to have thin aluminum parts, so you can penetrate them, and and titanium and things like that are really good. They really fit eddy current well. So eddy current's extremely fast. It can find surface breaking defects and subsurface defects very fast in aluminum skins and landing gear and things like that. So you see it a lot in the aircraft industry. Oh, I think I kind of covered most of this. So eddy current's extremely fast. We're pulsing in the megahertz with eddy current, so it can be done very fast. It can be done at really high temperatures. There's eddy current inspections being done in steel mills where steel is red hot, and they're inspecting it right away. And if there's a defect, they don't have to heat it up to melt it down. They can just put it right back into the furnace. So it can be done at extremely high temperatures. It's really good at complex geometries because you can curve those coils into any configuration you want. And it's great at detecting surface breaking flaws. And the limitations, being limited to thin materials, and it also doesn't work on carbon steel well. So as soon as we say we have thin materials and it doesn't work on carbon steel, it really kills it for most of the Alberta applications. All right, so that's the 5 basic NDT techniques that are governed by the government of Canada, and those are the common ones. And you'll see those quite. Other than eddy current, you'll see all of them regularly. Now, when Patricia and I first talked about this, he wanted me to put some advanced techniques in. So I picked two that are very common as well. So I'll spend a bit of time talking about phased array inspection and then a bit of time talking about digital radiography. So with phased array inspection, it's really the same as ultrasonic inspection, except we don't have a single piezoelectric crystal, we have many. So all of that stuff that I already talked about with ultrasonic testing, there's one piezoelectric crystal and you put it into an ultrasonic probe and that gives you one sound beam. So by that I mean there's one frequency, there's one angle, there's one beam properties in terms of whether it's spreading quickly or not spreading. It might have a focus. All of that, you just get one property out of the probe and it never changes. With phased array, we take the piezoelectric crystal and we cut it into many small pieces. And that gives us the ability to control the sound beam or engineer the sound beam. And that's why people like phased array, is not because it does anything different than regular inspection. It's just because we can engineer the sound beam to fit whatever inspection we're doing. And I put some examples of probes at the bottom. The one on the far right is by far the most common one in our industry, and that's called the linear array. And then the one in the middle is a 2D array. That's like, and then the one on the left is an annular array. But the one on the right is the one we see by far the most in Alberta. So all we're doing here is, this is kind of a complex picture, but all we're doing is we're sending delayed sound pulses to the different crystals. So we've taken the one big piezoelectric crystal, maybe we've cut it into 16 small ones, and we're sending delayed pulses to those crystals to engineer a sound beam that fits whatever inspection we want to do. That's on the emitting side. So that's generating the sound beam that's going to be in our part that we're inspecting. And then on the receiving side, we can do the same thing. We can apply time delays on the receiving side to whatever signals we reflect from flaws. So that's what phased array is. And I know that's kind of a complex figure and it's kind of hard to understand, but so this is essentially the word part of that figure. So what we're doing is we're pulsing those elements on different time delays. We may put different voltages on the different elements. And we may, on the receiving side, when we get reflections from the material, we may put different gains. So we may amplify signals used at, we may amplify the signals from different crystals differently. And when we do all of that, what we're doing is we're generating a focal loss. So that might be, we're generating a beam that has a certain angle, a certain focal property, a certain sensitivity to a certain type of defect. And this is probably where it kind of hammers home. So what we can do is we can generate different sound beams by pulsing those crystals and receiving the sound in different ways. So in this case, what we're doing is we've got a bunch of different elements, but we're only firing 4 of them. And because we're only firing 4 of them, we can move that sound beam back and forth electronically. So if I was doing this with a regular probe, I'd have to move the probe by hand, whereas now I can control it electronically. So that's useful. So I can, all of a sudden I can do this electronically, which means I can do it super fast and well controlled. I can also generate angled sound beams. So suppose I pulse, those little pulses show the time delays I'm giving to the crystals. So if I start to delay the sound to adjacent crystals, I can generate an angled sound beam. So that means I'm pulsing, crystal number 1 a little before crystal number 2, and then I'm pulsing crystal number 2 a little before crystal number 3, and all the way down the line, I can generate different angles. So for the same probe, I can now move the sound beam back and forth, and I can generate any angle I want. And the other thing I can do is I can generate different focal properties. So here, what we're doing is we're pulsing the outside crystals before the inside crystals. And that generates a converging sound beam, which means I'm focusing it. And I can change where the focus is. I can change what the depth of field is by just pulsing these crystals differently. So I got a question here. What are the typical size of one of these units? So the probe for a standard ultrasonic probe, it might be something like 10 to 15 millimeters in diameter, something that's easily held. A standard phased array probe would be maybe 25 millimeters long and maybe half or 10 millimeters wide. And inside that would be 16 elements. So it's a little bigger, but it's certainly not 16 times bigger if you have 16 elements. They cut these individual elements pretty small. And then with phased array probes, we can get all kinds of different sizes. So we can have 16 elements is about the smallest they produce, because that gives you anything smaller than that, you just can't generate these kinds of sound beams. But you can go up to 256 elements. And at that point, it's such a big probe that nobody would be holding it. It would be on a robotic arm or something like that because it's too big. So hopefully that answers that question. And the real power of phased array is we can do all of it together. So we don't need to just move the sound beam and then do a second inspection where we have a different angle, and then a third inspection where we have a certain focal property. We can apply all that at the same time, and we can generate a sound beam that has a certain distance from the weld, a certain angle, and a certain focal property. And then we can generate another beam that might be a little different. And we can generate hundreds of these beams. So what we can really do is engineer the sound for the inspection that's being done. And that's really what we like phased array for, is we can look at a component, we can figure out where there might be a defect or how we're going to inspect it, and we can generate a really nice inspection plan using the different sound beams to cover the whole area. So advantages and limitations we have. So phased array doesn't do anything different than regular UT. It's UT, ultrasonic waves or ultrasonic waves. It just, with phased array, we have the ability to engineer the sound beam for our inspection. And it's usually easier to interpret. When we have a full picture of everything that's going on, it's easier to interpret than that first image I showed you, the A scan. So it's good for interpreting. And then limitations, it's harder to find people that are trained in this because it's an advanced technique. It's far more difficult for our customers to interpret the data because they don't have the training, so it's hard to interpret it. Those are typically the problems we have, or getting enough people to do the work and having customers that understand the results and trust them. All right, so the last technique I'm going to describe are the digital radiographic techniques. And if any of you have been unlucky enough to break an arm or a foot or a leg or something, you've gone into the hospital, and they don't have film anymore in hospitals. They have radiographs that come up on screens, and that's a digital radiography technique. So rather than having a piece of film that we have to actually do a wet chemistry and develop it and then have a piece of film, we can do radiography with computers where we have all the images on a computer, and that brings all the image enhancements to the table that we're used to seeing, right? We can do edge enhancements and color enhancements and darkening enhancements. And so we can pull a lot more information out of the radiography techniques using this. So with DR is digital radiography, and that's a lot like what's in your camera. So with digital radiography, we have a small, inside your camera is a small array that's light sensitive. And when you buy a 20 megapixel camera, that means there's 20 million pixels in that camera, and they all respond to light, and they build up a digital image of whatever you've taken a picture of. This is exactly the same, except it responds to high energy radiation because we're using high energy radiation rather than light. So these techniques are done a lot like film. They work with gamma sources like iridium. They work with X-ray tubes. They work with LINACs, which are linear accelerators. We expose them much the same way as film, except We usually get poor spatial sensitivity, and that means we have less ability to find really small defects, but we have really good dynamic latitude and really good contrast sensitivity. And dynamic latitude is the ability to see many different thicknesses in the same radiograph. So we're far better than film with that. With film, if we have, say, a part of a casting that's small and a thin and a part of a casting that's thick, we have to take two different radiographic exposures. With this technology, it's almost always one, and that's dynamic latitude. And then contrast sensitivity is the ability to see small changes in grayscale. And this technology is much better than film at that. And then there's a second technology called computed radiography. So digital radiography is like your camera. Computed radiography has a piece of, we call it a plate, an imaging plate, and it's almost like a film, except it's reusable. So for film, we use it once and then we develop it and we never use it again. With computed radiography, we take a piece of film-like material out there that we call an imaging plate, and that has a phosphor compound in it. We expose it the same way we would do film, but when we bring it back, we run it through a laser scanner, and that pulls the image off of it using photostimulated luminescence. And we get a digital image on the computer, and we erase that plate, and we can use that plate forever. If we don't damage it, the phosphor compound will last forever. So we can take that out into the field, we expose it exactly like a piece of film, we bring it back, laser scan it, and we get a digital image. And this is the digital radiography, the detector arrays. With this, this is exactly like your camera, except we use scintillators because we have to convert the high energy radiation so the sensors can read it. And your camera will have a very small sensor in it with 20 megapixels. These have to be big because we're inspecting castings and big rubber parts and composites and all kinds of other stuff. So typically for us, the sensor spacing would be something like 200 microns, and we would have a 14-inch by 17-inch panel with all those sensors in there. And these are extremely fast systems. So with computed radiography, we expose it a lot like film, and we like it because it's the same procedure as we're used to. With digital detector arrays, we like them because they're fast. They're about 10 times faster than film. So we can take it into a customer site and be 10 times faster, which customers love. So for the right applications, we can be really fast. But these systems are breakable, kind of like your camera, right? You drop your camera and you're done. You got to go buy another camera. These things are worth $120,000. So if we drop them, we've got a problem. But customers do like them because they're fast. So we take them out in the field, and we do work with them. We shoot castings with them, piping, all kinds of stuff. But we have to be very careful because if we end up freezing them or we end up baking them or dropping them, then it's a big bill. And like I said, with these digital radiography techniques, so computed radiography, CR and DDA, they generate digital images, and we can pull a lot more information out of a digital image than we can out of a piece of film. So all the standard stuff you'd expect. We can do edge enhancements. So suppose we're looking for cracking in a casting and the cracking is fine. We can apply edge enhancements to try to bring out edges to find cracking. Window leveling is the ability to look at certain parts of the radiograph. So suppose we have thin parts in a casting, medium thickness parts, and really thick parts. We can do one shot, and then we can window level it to only look at the thin part of the casting, and we can inspect that whole thin part of the casting and produce a radiograph for a customer to look at. We take the same radiograph and we can window level it and look at the medium thickness parts. And we can do our interpretation, produce a report and an image for a customer. And then we can window level it a third time and look at the thick parts. So that's a really powerful technology that allows us to take inspections that would take many different exposures and do it in one exposure that's 10 times faster. So one of our successes at Iris NDT is we took a casting that it took 16 exposures. We did it in 3, and those 3 were 10 times faster. So really, it's 0.3. So we went from 16 exposures to less than half the time, less than the time it would have taken us to do, less than half the time it took us to do one exposure. So it's like 30 times faster. So for the right application, we can do really well. And then I thought I'd throw some pictures up of what these look like. In this case, we've done an inspection on a pipe. So this is the pipe here. This is insulation around the pipe to keep it from, that's to keep the heat in. It's really common. Almost everything in Alberta is insulated. So this is the insulation. This is the aluminum banding that holds the insulation on the pipe. You can see that. This is a comparator ball. So this is a known diameter that allows us to scale the whole image so we can get the right thicknesses. And here, this is the pipe. That's a weld on the upstream side of the elbow. And all of this is rust that's being held against the pipe by the insulation. And this lighter area here is the thickness. So, here we've got 192 thousandths of an inch. There we've got less than 100, and here we've got almost a millimeter. So this is incredibly bad corrosion. And then all of this is we've just zoomed in on this area and we've window leveled it to show that thickness, and we've ignored everything else. So a nice technology where we can, we don't just give a customer a picture, we can zoom in, give them a second picture, change the window leveling to optimize it. And all of these are cracks in the rust. They're not cracks in the steel. There's so much rust here that it flakes, it spalls, and that's spalling in the rust. And that's the insulation support band. And the insulation support band comes here, but we can't see it anymore because we've window leveled it out. The data is there. It's just we're not showing it anymore because we want to show this. So this is a weld inspection. So in this case, this is the base plate of the weld. And this is an 8-inch standard pipe. So 8 inches in diameter and 0.322 inches thick. So in this case, this is the base material. We have a weld reinforcement on the outside of the pipe, but we also have a weld reinforcement on the inside. So this here is the weld reinforcement on the outside. And then this is where there's a double weld reinforcement for the radiograph. So that's where we see the outside weld reinforcement and the inside together. And then this is our sensitivity. These are the wires on that penny. And we want to be sensitive to about 2%. So about, we can just calculate it, right? 2% of that is what we want to be sensitive to. And this is an ASTM B penny. So there's a bunch of different wires. They don't all fit in one penny. There's 4 of them. There's an A penny, a B penny, a C penny, and a D penny. And for this is the right thickness for this inspection. And then this is another one I throw on here. This has a C penny because it's a thicker weld. In this case, this is the base material, which is darker. This is the weld reinforcement, which is white because it's a thicker material, which means less radiation gets to the film. And this is actually, we've cut notches in this to be a UT calibration block. And these are tungsten rods in the middle of the weld for a UT calibration block. And then this is another inspection where this is the idea of averaging. So I think you guys have probably, or you people have probably covered averaging, where your signal to noise goes up as 1 over n squared. So the more, if you've got random noise in your system, the more averages you do, the better your signal to noise becomes. So in this case, we've averaged more and more, and you can see how these images just sharpen up. So with the digital techniques, we can do that. With film, we can't. But with digital techniques, we can really sharpen the image by averaging and reducing the random noise in the system. So advantages and limitations of this technique. It's got all the same advantages and limitations as regular radiography. So it's still going to be slower on thick materials. It's still going to be fast on thin materials. We still don't have to worry about surface condition, but we're going to get exposure reductions compared to film. And in some cases, it's dramatic. We're going to have digital content, which is really good for producing reports and archiving. So we're going to have great ability to compare inspections year by year. And then limitations, where it's more expensive, it's more sensitive to scatter, so we have to be more careful with scattered radiation. We need power on site. So that's how it would compare to the radiographic techniques. And then that's it. So I don't know if you guys or you people have any questions.
Thank you very much, Eric. This is fantastic.
Sorry for being so fast. It's a lot of materials.
Yeah, I gave him a heads up. This could have been a whole course, but it's better that it's one crazy class than nothing. And uh, so to everybody in the class, given that we have a shy of 10 minutes, if you wish, this is your chance to go and look at the old exams and look at the NDT questions. And if any of those questions you feel you you'd like to follow up, here we have Eric that is a million times better than anything I could tell you. How about that? So, Eric, yeah, stay with us for a couple more minutes. Chances are that there'll be some question.
Hi there. I have more questions. Thanks for answering all my questions. I was just wondering, like, in terms of your career itself, how you got involved in NTD and what is typically your role within it.
It was by accident. I came out of U of T with a PhD in physics. I had two young kids to support. One was, I think, 6 months old, and the other one was 14 months older than that. And I needed a job. I put out a ton of resumes. Most of them were completely ignored. I got a call back from a company doing NDT, so I went to the library, spent a whole week researching NDT in my evenings, and they liked me in the interview, and that was almost 25 years ago. So that's how I got into it. So no, nothing big there. And then in terms of what I've done, I started out spending a lot of time in NDT for many years. So I spent time in ultrasonics and radiography and guided waves and lasers and all these things. I spent years doing that. And then it became more and more important for us to start offering more engineering services because our customers were getting the NDT data, but that didn't tell them what they needed to know. It told them if they had a flaw or not, or discontinuity or not, but it didn't tell them if whatever they had was fit for service. So I was the one that started to talk to engineering companies, and then I was the main person that led to a big acquisition of an engineering company. And then I spent 5 or 6 years working with the engineering company, and I managed the group for a while and trying to integrate it into an NDT company, because that's a extremely difficult thing because culturally they're different and the people are different and the work is different. And so I spent a long time with that. And then we expanded geographically. So I was involved in our Australian and our UK expansions. And then it became important for us to offer mechanical services. So our customers were saying, you're going to do all the non-destructive testing and you're doing the engineering, but we need you to replace the insulation, and we need you to tell us if the insulation is good and work on the electrical and do some structural steel welding and clean surfaces. So I got involved in that. And then the last couple of years, it's been more about data. So our customers have been, especially in this environment, it's such a difficult environment right now with the price collapse and the politics and COVID. And COVID is not the biggest problem, but so I've been a lot more involved the last couple of years in the data side. So how do we take this data and we actually put it in a format where we can add value and we can do analytics on it, predictive analytics, and how do we work on digitizing processes and dropping costs? And because our customers have all asked us for a significant drop in cost, but they want better data. So the only way to do that is to really think about it in a different way. And so we've been digitalizing our processes. So that's been my main thing the last couple of years.
Okay, great. Thanks for the talk.
Oh, thank you.
if no one has any other questions, I still have one more question, which is I'm still like just thinking about this fitness for service thing, and like how you said that everybody still wants their, you know, whatever it may be that's getting tested to be fit for service. But yet at that time, the codes and standards don't apply anymore. So how do you even decide that it is fit for service?
What companies will do is suppose we say let's look at landing gear on a plane. So that's something they inspect a lot because it's there's huge stresses when planes land, right? So they know what parts of the landing gear can be susceptible to cracks. So they inspect planes in between, at night. So they inspect a plane and they find a crack in the landing gear. So obviously they can't send that plane up and kill a bunch of people. That's very bad. But they also don't want to take that plane out of service because that causes a cascading problem through their whole network, right? So they need good data on how big that crack is, where it is. They need to know for sure it wasn't there the last time they did an inspection. And then they can do a calculation. They can say, that crack is in a material that has a certain strength. It has a certain ability to resist that crack. Maybe we're going to fly it in a certain environment where it's at a temperature, because a crack at -40 is totally different than a crack at +40. And they're going to do a calculation that says they either have to take that plane out of service immediately because the crack is serious and they can't fly it, or maybe they can say that they can fly it for a week and take it out of service sort of at a regular interval. So they're going to do a calculation that looks at the strength of the material, where the crack is in that landing gear. They're going to do a full finite element a full finite element analysis, and they're going to get a result that says they can either fly that plane for another week, or they can fly it for a month, or they have to take it out of service right away. And the NDT, the part the NDT fits is only, it tells them where the defect is and how deep it is. That's all the NDT does. Everything else is an engineering task. Does that make sense?
Yeah, okay, thank you.
And it matters, the material matters, the strength of the material. There's something called a resistance to cracking, because some materials will be brittle and they'll crack fast. Other materials are more ductile and they'll crack slower. So that comes into it. The size of the defect, even the type of plane, right? A big heavy plane that's maybe flying in places where you're going to have storms is going to hit harder than a plane that's lighter, and maybe you're flying it in places where you don't have thunderstorms. And temperature matters a lot because materials have different brittleness at different temperatures, and you can do a calculation, and all the industries do that. So oil and gas does, mining does, petrochemical does. I don't think you can drive over a bridge in Edmonton and don't see corrosion. So they're all doing it for bridges, right? They're all corroded. So someone's deciding, is that corrosion bad enough that I better replace the bridge, or can I drive on it another year or 10 years? Or so
Yeah,
it's done in.
Oh, sorry. I would just say it's really interesting to think about like a company that does NDT tests, or NDT like provides data, and then essentially we're trusting engineers to make good judgment and good decisions with what they have in terms of data.
It can be a little scary at times, but every time you get in a car or drive over a bridge or get on a plane, or it's all someone is behind the scenes, deciding if, because I think defects are very common, right? So it's someone's in behind those scenes deciding whether that defect is okay or needs to be fixed. And I always come back to, society's pretty safe and things aren't blowing up and falling out of the sky. So I think people do a pretty good job.
Yeah, definitely. Good to know. Thanks.
Well, everybody, thank you, Eric. Thank you, Jolene, for these questions. We're putting Eric's time to good use, and we should all know that next time we talk to Eric, we are going to be built big bucks. So this is great that you're doing this for us. A million thanks, Eric. The timing was perfect. For all the students in the class, please know that everything that Eric discussed today is part of the quiz 2 on Tuesday, and you'll see some questions from previous years uploaded. So it's time to stop. Thank you so much, Eric. Thanks a lot.
No, thanks, Patricia. You guys all take care.
Until later. Bye-bye.